Hello and welcome to Lesson 1, Use a Logarithm to Solve for Time. Our objectives are to convert an exponential function to a logarithmic function in order to solve for that exponent, which is time. We are also going to be using a natural log to solve for that exponent as well. And you can see three examples of the time value of money problems, or the formulas that we use for those problems, below. Here, this first one is a very simple one, assuming annual compounding, because if you'll compare it to this bottom one, there is no r over anything, or up in the top we just have n versus nt. We put in the n, or the extra n up here, when we compound more than once a year. And then this formula over here represents continuous compounding. And we've used all three of these in order to determine future values of money. Okay, so let's first review a little bit about logarithms. When we're looking at logarithms, we start off with an exponential equation that we would convert to a logarithm. And the reason is because if you have something like 2 to the x equals 8, how do you figure out what x is? You can't divide or multiply or take the square root of anything in order to solve for x. The only way to solve for x is to turn it into a logarithm. Now this one, you know what the answer is. 2 to what power equals 8? That's pretty easy. 2 to the third. But what if we had 2 to the x equals 11? You would not be able to do that in your head, and you definitely couldn't do any traditional math to figure that out. So that's where the logarithms come into play. Let's convert this to a logarithm. There's a few ways to do that, but probably the easiest way is to just multiply both sides by a log. So let's do that. Let's multiply the left side by log. So we have log times 2 raised to the x equals log 8. Okay, now we need to solve for x. We can do that. So as soon as we convert this to a log, this x up here can come down to the front in what is known as the power rule. So anytime you an exponent in your logarithm, you can always bring it down to the front of your log in what is known as a power rule. So instead of raising the log of 2 to the x power, we would have x times log 2. So we can write that then as x log 2 equals log 8. And now we can use our traditional math to solve for this. So how would we solve for x? How would we get rid of log 2? Well, that's easy. We would just divide by log 2, which means we would need to divide this side by log 2. Looks complicated, but in fact it's not. It's pretty easy to put in our calculator at this point. So log 2 divided by log 2 is just 1, or 1x. And now we're ready to put this right side in our calculator. So let's go ahead and look at our calculator. I've put up a site here to help you because not everybody has calculators that have logarithms. But this is a website that has a scientific calculator with logarithms to help you. And I will put it on your assignments as well so that you can link to it. So going to our calculator, we had log 8 divided by log 2. So we look on our calculator. Here we see a log. There's also a natural log, which we'll use with e. This log assumes a base 10, which anytime you don't see a base, you assume a base 10. But this is exactly what we're looking for. So we would hit the button log, and notice that log appears here. And if you go back and look at our equation, again, we have log 8 divided by log 2. So I would type in an 8, and my parentheses, a backslash for divided, hit the log button again, and then a 2, and parentheses. Now when I hit return or equals, I get my answer, which is 3. And that we know is correct. So x is equal to 3. All right, let's look at how to do one that has e, that has a continuous compounding number in here. Anytime you see the e, you should think to yourself, I'm going to now use the natural log. It's much more convenient. I can, of course, use the standard log if I'd like, but anytime I have e, the natural log will make it easier. So let's look at that. Once again, I'm going to multiply both sides by log, but instead of standard log, I'm going to use the natural log. So that's ln. So ln times e to the x equals ln 130. Now if you remember back when you did logs, if you have ln, ln is the same thing as log base e. Well, if I were to write it like this, you can remember that if the base and this number are the same, these just cancel. They turn into 1. So essentially what I have, if I use my power rule, remember this exponent can still drop down in front here, and I would get x, and this stuff, log base e to the e, or natural log e, just becomes 1. So I'm left with x on this side, and the natural log of 130 on the right. So again, remember, anytime you multiply the natural log by e, that goes away. That becomes 1. And I'm left with x. So now all I have to do is put in the natural log of 130 into my calculator in order to solve. So let's go back to our calculator. If I type ln this time instead of log, so now I'm using ln, and I type in 130 and hit return or equals, I get 4.8675. Let's go ahead and round that to the hundredths place. So that would be 4.87. The 6 would round up to the 7. And in this example, x equals 4.87. So that's a quick review on taking two exponential equations and turning them into logs in order to solve for the exponent. Let's go ahead and apply that to what we are looking at. Let's take these two examples here. In this first one, we have a future amount, 1790, and we have a current amount. We have our principal, the amount we currently invested. And obviously we're using compound interest because we have the E at a rate of 4%. And we want to know how long do we need to invest our money, our $1,200, before we have 1,790 sometime in the future. All right, so let's think about this logically. Before we start using logs, we want to do everything we can that's conventional. Well, I can take this 1,200 and I can divide both sides by 1,200. So let's go ahead and write our equation. 1790 equals, so what I've done is I've written the equation and I want to get rid of this 1,200. I want to move it to the other side because my goal is to get t by itself. I can divide the right side and the left side by 1,200. Now I could leave the left side like this, but I'm going to go ahead and simplify. So let's go back to our calculator and do 1790 divided by 1,200. So 1790 divided by 1,200 gives me 1.491. How about if we round to 1.5, just to make it a little simpler? So I've got 1.5 is now equal to e raised to the 0.04 t. Remember, anytime I have e, I should use the natural log. So let's go ahead and multiply both sides by the natural log. So natural log of 1.5 is equal to the natural log of e raised to the 0.04 t. Okay, remember the power rule. I'm going to take this power, this 0.04 t, and I'm going to drop it down in front and make it be a factor instead. My new equation then will be natural log 1.5 equal to 0.04 t, and then what happens to natural log times e? That goes away, so that's gone. Now it's pretty easy to solve for t. All I have to do is divide by 0.04 and divide the left side by 0.04. 0.04 and 0.04 gives me 1, so this side is just t, and then I just need to put the natural log of 1.5 divided by 0.04 into my calculator. So let's go ahead and do that now. Natural log of 1.5 divided by 0.04 gives me 10.14. 10.14 years. So that's how long it will take for my money, $1,200 to grow to be $1,790 at an interest rate of 4% compounded continuously. All right, let's try this one down here. This one's a little bit different, but still the same principles apply. We should do everything we can before we take a log. So first things first, let's write out our problem. Okay, what can we move over from the left side to the right side so that we can start to get t by itself? Hopefully you said 3,200. We can divide both sides by 3,200. Let's go ahead and do that. So in my calculator, I'm going to divide 5,000 by 3,200, and I'll get 1.5625, and I didn't round quite as much there. And then on the right side, the 3,200s cancel. I can add the 1 plus the 0.07 because they are in parentheses together, and then raise to the t power. Well, I'm ready to go. All I need to do now is multiply both sides by a log, so I can multiply this side by a log, and I can multiply this side by a log. Remember what happens to the t, my power, based on my power rule, this t can drop down in front, and on this side I will have t times the log of 1.07. And on this side I'm left with still log of 1.5625. And I'm ready to isolate t. I can get rid of this log of 1.07 by dividing both sides by the log of 1.07. These cancel, and I just have t now on the right side. So t is going to be equal to the log of 1.5625 divided by the log of 1.07. So let's go ahead and do that. Okay, so I've got the log of 1.5625 divided by the log of 1.07, and when I hit return, my answer is 6.596 years, or we'll round that to 6.6 years. So 6.6 years. I will have earned, or my money will have grown to $5,000 if I invest $3,200 at a 7% interest rate. So that will take me 6.6 years. All right, we have one final example to look at, and this is our third type of equation where we actually compound. So now what we're looking at is this equation here on the bottom. Let's go ahead and use this equation to solve this problem. Let's first identify what each of these is. So A is our future value, and this 12,400 represents our future value here in this problem because we're looking for our money to grow to be 12,400. Then P is our initial principal, which is 8,000, which is what we initially deposited. R is our interest rate up here, 7%. And it says annual interest compounding quarterly. So our compounding periods are quarterly, and that's our N. Let's go ahead and plug everything into our equation. We have 12,400 future value is equal to our initial principal of 8,000 times 1 plus our rate, written as a decimal, and we compound 4 times a year. We compound quarterly. Raised to the nt. The number of times we compound per year is 4, and we are trying to solve for t. Let's begin. If you want to go ahead and pause this and try this on your own, go right ahead. You should get about 6.3 years. Let's see if we can do this together after you're done. Okay, so we should have divided both sides by 8,000. 8,000 divided by 8,000 is 1, or that's gone. So then our right side, we are left with 1 plus 0.07 divided by 4 raised to the 4 times t power. If I take 12,400 divided by 8,000, let's see what I get. 1.55. Okay, let's simplify this a little bit more. Let's simplify the parentheses. So let's take 0.07, divide that by 4, press equals, and then let's add 1, plus 1. So that gives me 1.0175, and I'm being careful not to round too much so that I can get a little more precise answer. All right, now we're to the logarithmic time. We just need to multiply both sides of these by the log. So let's multiply the left side by a log, and we'll multiply the right side by a log. Now once we've done that, remember that we can use the power rule here, 4t, to bring it down out of the exponent position, which is what we're trying to do. So the left side becomes 4t times the log of 1.0175. Remember, that's the whole point of turning things into a log. That way we get the exponent down out of the exponent position in order to better solve. All right, we're getting close. So now what do? Well, we need to solve for t, so we need to divide this side by 4, because we don't want the 4 there, and by log 1.0175, which means we need to divide the left side by the same thing. All right, so what cancels here? The 4's cancel, and the log cancel. That just leaves t. On the right side we have t, and now on this left side here we have log 1.55 divided by this. So let's go ahead and pull up our log calculator and figure this out. I have typed in log of 1.55 divided by, and I've put this in parentheses, the denominator, since I have a little bit more in the denominator than usual, 4 times the log of 1.0175. When I press equal, I get 6.315, which we said should equal about 6.3. Okay, and that concludes our lesson today on how to use a logarithm to solve for time. So remember that you have 3 examples here. We have one example where we compound annually. We have another example where we actually have compounding periods throughout the year, and then we have our continuous compounding example. Remember that all we're doing is multiplying the left and the right side by a logarithm in order to take our exponent and bring it down using the power function. So hopefully now you're able to convert an exponential function to a logarithmic function, as well as use a natural log to solve for time.